So a brief outline, I'm going to first provide a motivation, an overview of what I'm going to talk about and some of the technical concepts at a high level. Then I'm going to go into some details about Snorkel, the new system that we've been working on. I'm going to talk about data programming then, sort of what's under the hood powering it. And then briefly at the end a bit about current directions. And I guess that's where you guys come in as well, so hopefully that'll lead into discussion. So first, Chris presented some of the exciting work that's been done in the lab on predicting small cell lung cancer outcomes using histopathology slides and other data with some of our collaborators who are here. And this is a pretty exciting problem. It's pretty critical for automatic detection of these types of diseases and for precision cohorting. And it's interesting that, as Chris mentioned, pathologists only agree in about 60% of cases when assessing the tumor stage. So there's room to improve here with automated methods, or at least that's our thinking here. So what does a basic approach look like? We take unstructured input data, we train some sort of machine learning model, and we get out some sort of predictions. Here it's a Cox model about patient outcomes. And the exciting results that we've gotten are that we can match human accuracy in the tumor stage prediction and surpass it in actually the survival prognosis prediction. So what does a typical machine learning pipeline look like, such as what we started with here? First, we have to get some sort of hand-labeled training data. And in the cases that we work with, this requires domain experts to actually sit down and read through volumes of data and annotate it by hand. And then we have to have people, like machine learning experts, if we can call ourselves that, who sit and in large part do feature engineering, trying to pull out the important facets of the data that should be considered by the model. And then data goes in, predictions come out. And in this process, the training data curation and the feature engineering are sort of the two traditional development bottlenecks that people who apply machine learning systems face. So one exciting development that we've observed and been engaged with is the rise of automated feature generation techniques. So these can now dream about cats. They can do other things too. They can make these pipelines significantly easier for users given enough labeled training data, which is the catch. So we see huge empirical gains using methods like deep learning approaches if we have lots of hand-labeled training data that's curated at great expense. So this new pipeline looks like you have a crowd of domain experts or lay annotators, if that's okay for your task, create large-scale training data sets. And then we no longer necessarily have to do feature engineering, at least on a first pass. But what essentially happens here is that we've shifted the pain point to this labeled training set creation. So Chris stole my favorite catchphrase, but training data is sort of now the new limiting reagent in these systems. And what are some of the drawbacks more precisely? First of all, it's expensive, especially when domain experts are required, which is sort of the regimes that we work in. I mean, we consider all of you guys domain experts as well when we're working with your problems. And so this is tougher than just putting up something on Mechanical Turk for lay annotators to go over. It's slow. Actually, we spent a lot of effort on actually working out the guidelines. I think for some of the benchmark tasks, there are 50-page guidelines for how to annotate things properly. And there's still always inter-annotator disagreement. So it's an involved effort. And somewhat critically, it's static. So as you're working on applications that actually interface with the real world, especially I'll talk about extraction applications like Chris mentioned, the scheme of what you actually need to pull out changes. The data types change, and other aspects of it evolve. Training sets do not, and we want to have some better method than just throwing out a training set and creating a new one when the drift is too great. So what I'm going to talk about at a very high level is this idea of weak supervision. And this is the concept that we can take various signals that are less accurate or reliable than sort of ground truth data where an expert sat down and annotated by hand, possibly multiple diverse signals that conflict, and use them to still train high-performance models. And this subsumes a lot of ideas that have been in practice, especially in the natural language processing community, like distance supervision. I'll talk more about these later. Crowdsourcing, if applicable, ensembling classifiers together, using heuristics to create training data. And so we think that we can generate large training sets programmatically this way, but there's always going to be noise in these training sets. So how do we deal with this? And our approach, which I'll go into in more depth later, is that we can have users express heuristics and these weak supervision signals as functions that label data, that these can be applied to large volumes of data to generate large, albeit noisy, training sets, and that we can then automatically denoise these training sets to some degree by modeling them as a generative process of training set labeling. And the sort of high-level theme here is that we think training set creation deserves to be, to get focus, to get serious technical focus as the new key development bottleneck for these ML systems. So in our view, the new pipeline looks something like this, where you have domain experts who are iterating on sort of very tangible functions, say Python functions they're writing in our Snorkel framework. These are then denoised and modeled, and then used to train a large neural net or something equivalent. So we're excited about this potential new approach to building ML systems, and we've been deploying it. So now I'll give a little view of what this looks like in practice. Some of you actually in this room have been playing around with Snorkel with us, and we're, again, really grateful for the feedback and the experience. And it's all open source, so you can check it out. We have tutorials up. And I'd like to point out that a number of my collaborators are here today, so you can go up and approach them, and they'll be at the poster session and giving talks. A guy in the end might be a grad student, I'm not sure. He hangs out in my office sometimes, and he has good ideas. He'll also be happy to talk about this. And especially, we're very thankful to our sort of core collaborators, such as Emily and Allison, who talked earlier. So Snorkel is focused around this task of dark data extraction, or otherwise known as knowledge-based creation or construction or information extraction. Our goal is pretty simple at a high level. It's just to populate a fixed schema with structured data pulled out of unstructured sources. So taking something that looks like text, sensor data, time series, images, and pulling out some aspects of it that we care about, often entities and relations, like Emily was talking about, and putting it into something that looks like a relational database, or that is a relational database, or looks like an Excel spreadsheet that we can then use for downstream analysis. And it's a critical component. These are some of the previous projects we've worked on as a lab with Deep Dive in law enforcement pipelines for anti-human trafficking, in assembling large knowledge bases for pharmacogenomics, in doing climate paleobiological analyses from the literature. And having this intermediate structured representation of data is sort of a critical component of a lot of downstream tasks, such as doing macroscopic analyses of the climate, doing link prediction between protein-protein interactions, doing predictive modeling for disease outcomes in the clinical setting, enabling entity relation-centric search, for example, supporting law enforcement, and many others. So here's a concrete example that some of us are working on right now, which is just extracting mentions of when a chemical is linked to inducing a disease from the scientific literature. So this process kind of looks like we find entity as our sort of mentions of entities in the text. Here are chemicals, diseases, and we just want to pull out the relations that are actually asserted and put them into a relational database. And the traditional machine learning approach, again, is someone has to define these sort of candidate facts. Someone has to label a training set by hand, define features by hand, and then we do learning and inference to find the end extraction. So this is sort of what it looked like for a long time and what we're trying to move on from. And we think that we can make radically easier to use dark data systems, first of all, by using the methods that I was going over at a high level, and also by focusing on sort of core use cases, which is part of why we're so excited to work with you guys to help define that. And our stretch goal is to make this usable by non-CS PhDs on like very tight deadlines with very real applications. And we're having some progress there, so we're very excited about that. So what does this actually look like? Someone comes up to Snorkel, loads in unlabeled data, writes a set of labeling functions which express various heuristics or leverage these weak supervision sources to provide some signal for the model. This could subsume hand-labeled data as well. Then they choose a discriminative model. It could be some neural net. It could be logistic regression over some generic feature set. And then Snorkel takes care of actually creating this training set by applying the labeling functions, learning a model of these labeling functions to denoise this training set, and then training the end a discriminative model in a way that's aware of the sort of noise in the training set to some degree. And so this is really the main user input, writing these labeling functions, as you heard Emily and Allison talking about before. So I'll go into that a bit. So labeling functions are in a more formal sense, they're just functions that say yes, no, or abstain in the binary classification setting, which we'll focus on here. And we treat them pretty much as black box functions. We have some independence assumptions, but that can be relaxed. But basically, users can use traditional scripting languages to subsume a lot of these different signals just by expressing them as these labeling functions. And so I'll give a couple sort of high-level examples. So for this chemical disease task, one example is what's often traditionally called distance supervision in some communities. We can take an existing knowledge base where we sort of, some people by hand have said, okay, chemical A is known to cause disease B. And we can say something like, okay, if chemical A and disease B appear in this sentence, we'll label this true. And this is clearly not going to be right 100% of the time, but it also clearly has some signal, and it tends to be empirically useful. Similarly, we can use simple pattern-based heuristics. We can say if the word cause appears in between, then we should label this as true. And we can use combinations of these heuristics and distance supervision techniques and sort of combine them all under this simple framework. We can also define dependencies. If we know that one pattern looks for the word cause and one looks for not cause, we can actually add this complexity to the model in a very simple way. And it's still all done in standard scripting languages. And I'll point it. Yeah.
So you had two functions that were giving the same label. Is
Yeah.
there a preference or importance of one rule?
Yeah. So that.
Repeat the question.
Oh, sure. So sorry. The question is perfect, and I'll get into it in a little bit more depth later. This is: do we determine or ask for some sort of weight on the different heuristics of which ones might be more reliable? And so that's actually what our data programming method learns, or what we model, and actually learn automatically the weights of these labeling functions. So I'll get into that a little bit more in a second, but it's a great question. Some motivation. Oh, sorry, question. Yeah.
You also learn which functions are better in which regions of your feature space. For example, some of them can be better here, and then which ones more than.
Yes, exactly. That's actually. Oh, sorry. The question is, can we actually learn that some labeling functions might be more appropriate in different areas of the feature space? Like for certain examples, this labeling function is better at telling cats and dogs apart than, I don't know. I'm limited in my number of animals. I know. There are no other types of animals in deep net land. But you can imagine this, and this is actually some exciting work that's going on in the lab. Some unnamed person came up with the name Socratic learning, and this is where you, so one way that you could imagine doing this, of several that we're exploring, is that you actually have the discriminative model communicate back to the generative model. And so you augment the feature space of, I'll get into the, this will make more sense when I go into depth a little bit, but you have the model that learns the accuracy of the labeling function, can actually be augmented, so it's taken into account some of these features.
Yeah, because there is some work in crowdsourcing that actually tries to model that, so you can borrow something like.
Oh, it's a great point. I mean, so there's a deep connection here to an obvious parallel to crowdsourcing, where you're trying to estimate the relative trustworthiness of different crowdsourcers, and you also might want to estimate sort of latent groups or sort of expertise areas for them, where you should, certain areas you should trust them more. And so we'll talk about that more later. It's a great question. We're very excited about that area of inquiry. So a little application plug, something we're excited about now, and sort of trying to express why we're excited about these labeling functions at a high level, is that we think they make for a much easier integration of domain knowledge, which is often, in our opinion, the most important part of these of getting these pipelines running. So we, for example, have a very cool data set of a bunch of combat reports from insurgencies in the Philippines from one of our collaborators, Chris mentioned, at the Hoover Institute. And we're trying to analyze these to find out more about how insurgencies function. And if you notice, if you can see here, none of this is private, but there's lots of shorthand and code words and stuff that we don't know how to interpret or what we should extract. And our goal, again, is just to take something unstructured like this and actually pull out attributes that we want to analyze. And really what the whole game is about from this perspective is getting domain knowledge of what different types we care about or what different acronyms mean or shorthand means, and putting into the system and being able to quickly iterate on this. And that's sort of what we think labeling functions make very easy and tangible for domain users. And this is another picture of them from the tutorial that's online, where we're trying to extract people that are married from news articles. They're just Python functions. They can be more complex, but they're pretty simple to use in standard scripting languages, whether Python or other. So Also, a little bit of depth into how we're building Snorkel. And this gets into a question earlier about pulling out relations that are across sentences, or that might be longer range dependencies. And so we actually are thinking of unstructured data usually has some hierarchical structure, whether it's a set of documents or it's a set of tables. So we have a sort of generic data model for these dark data extraction tasks where we think of a hierarchy of what we call contexts and think of it in a generic way. Critically, every sort of level of this context hierarchy triggers a set of generic features in our system. So it makes it easier to leverage this hierarchy in the discriminative model. And then we think of candidates as the things that we're trying to extract. So we hope that this is sort of a generic data model that'll make it easier to build these systems. And we also have started focusing a lot on entity linking as the key integration task. So this is mapping the mentions that we pull out to some canonical identifier, whether it's a public medical ontology or some internal set of IDs, as sort of the central task. And focusing on this task, we can actually simplify the overall extraction task. And so that's another area that we're looking into. And we've had some initial success working with our bio collaborators. Jason will talk more about this. This is tagging diseases and chemicals, and we've actually been able to approach or even exceed supervised learning benchmarks where they actually did have this hand-labeled training set. So we're excited by these results. And what we're even more excited by is some of the projects that we're just beginning to start up and working on at our weekly hackathons. So this is just some of the people that have stopped by and that we're working with. We work with Baylor a bit on extracting protein-protein interactions, extracting cancer biomarkers with another lab at Stanford, drug-drug interactions, as Emily talked about, and adverse post-surgical events or data to support that sort of analysis, as Allison discussed. We're fortunate enough to have some people from Accenture come by most weeks, and we're working on customer support transcript extraction. And we're also talking with some cool initiatives around taking projects from the defense space and actually getting people at Stanford to work on them using systems like Snorkel. So we're extremely excited and grateful for these different opportunities. So I'll now go into a bit of what's under the hood of this data programming approach that drives Snorkel. So at a high level, the pipeline is that user comes, I'm going to think about this in terms of binary classification. In the dark data extraction task, this is just, I see a fact, I see a chemical and a disease pair. Does this belong in my knowledge base or not? Is it a true mention of something I care about? So we have some unlabeled data where we don't know the true labels. We have a set of labeling functions. And we might have a set of dependencies. We can actually, we have the theory and some of the machinery to handle these more complex specifications. I won't focus on that here, but it's exciting work in the lab. So at a high level, what we're doing is first we learn a generative model of the training set labeling process. So, and then we take the predictions of this model and we use this as a sort of noise-aware training set to train a discriminative model. And I'm just going to go through this quickly, but just as some intuition, we model the labeling functions in this initial approach as sort of independent voters that have some accuracy with respect to our task. And we look at what they're voting. Here, imagine green is positive and red is negative. And we look at where they overlap and where they conflict. And based on that, we learn the model of their accuracies. And so you can think of this majority vote intuition at a high level. And this is also similar to crowdsourcing. We have very different constants in that here there are a small number of labeling functions that are each labeling a large set of data points potentially versus the other way around. But it's a similar concept to how some of these systems work. And what this does is it produces a set of sort of more granular training labels. So instead of having just yes, no, and treating this as absolute ground truth, which is actually also a flawed approach when you're dealing with human annotators because they don't always agree and they're not perfect. We model these as probabilistic labels. And then we train what we call a noise-aware model. So a standard discriminative model where we're doing classification, we'd be trying to minimize the loss over the training set. So we're trying to minimize the number of examples that our model predicts incorrectly. And all that we're doing here is we're saying now we want it to minimize the expected loss with respect to these sort of probabilistic labels. And this is a very small tweak, so it's pretty easy to plug in any discriminative model or most to this framework, whether it's a neural network or whether it's a simple logistic regression model. Yeah?
Looks very similar to the adversarial distributed model that people use for generating images and text. Is this similar to that model?
So at a high level, oh, sorry, yeah. He was pointing out the connection potentially to these generative adversarial networks, where there's a generative model and there's a discriminative model, and there's sort of a min-max game where they're trying to, the generative model is trying to generate fake data, and the discriminative model is trying to learn to discriminate. At a high level, this is similar because we have a generative and a discriminative model that are interacting. Here, the generative model is just producing training data for the discriminative model. Some of the work ongoing in the lab at the poster session, you'll see they're actually communicating back and forth. That's the Socratic learning piece. So at a high level, yeah, there's a connection there. And be happy to talk about it more after the talk.
Same question. Labeling functions, I mean, they sound like they're features that are sort of manually programmed, or how do you look at the labeling?
So at a high level, I mean, the question is about labeling functions looking similar to features. And they are of the same basic functional form. In general, we think that the optimality criterion of labeling functions is a bit easier for users to interact with, because we just want them to label data correctly, whereas what makes a good feature is a little bit more of a complex question that needs to be evaluated in terms of end-to-end performance. That's one sort of practical distinction. And in terms of other stuff, I guess I could talk about it further afterwards.
Do you have any ground-truth label data?
So the question is, do we have any ground truth labeled data? So in the basic setup, no. Although this would be easy to integrate. So for the generative model, there is some work in the lab on integrating this and having an optimizer for when you should and don't need to. And then for the discriminative model, this can be integrated, for example, by having a labeling function that checks against labeled data. Yeah. Sorry, yes. We also validate against ground truth data. So this is very critical. We always need a small set of labeled data. Orders of magnitude usually smaller than we'd need to actually train a model, but to evaluate against. So we always do evaluate against hand annotated data. That's very critical. That's a different procedure. So there is validation data that the user can use during the labeling function development process, but that's not used directly in the generative model that learns their relative accuracies. Cool. Thank you for the great questions. I didn't repeat that last one, sorry. Okay, well, I'll get better at this, hopefully. I'll proceed onwards now, and I would love to, and others in the lab would love to talk to you guys about this, some of these great questions afterwards. So just a brief note that some of the theoretical results we have is exciting. There's more details in the NIPS paper that's up on arXiv. But basically, given some basic assumptions on having enough labeling functions that they basically overlap sufficiently, and that they are sufficient to sort of represent the true underlying class, we can dump in more unsupervised data and actually get sort of the same scaling with respect to reduction of training set error that we do with increasing the amount of supervised data in traditional supervised learning systems. So moving on. So the question is, small improvements. The question is, how do you know when you have a sufficient number of labeling functions to move onwards? And this is something, the easy answer that we use right now is we use end-to-end evaluation on some sort of hand-labeled data set. So we have a small number of hand-labeled examples, and we evaluate the end performance. That's the basic answer for right now. There could be other more creative ways. So the question is, will we learn new labels from the unsupervised data? So in the sense that we'll make predictions over this, over the unlabeled data, yes, that's the ultimate goal is to make predictions over a larger set of data points than the labeling functions cover. So the labeling functions, sorry?
Add to your labels, or is that
So we will not,
will you learn from your unsupervised data?
sure, so the question is, will we learn from our unsupervised data and add to our labels? So the approach is semi-supervised in the sense that you can feed in more unlabeled data and actually have the labeling functions be applied to this, creating more labels to answer your question. And then, yes, we hope we will learn from that. So there's some nice ability to scale, as I was mentioning, with the theoretical results that we get from this. And it's a good way to leverage this much larger set of unlabeled data that you usually have in a problem that you approach here.
Considering, because you're not going to have full coverage with your labeling functions, so to improve and build on top of it using like active learning or something like that to reach the classifier you want.
Yeah, so the question was about exploring new parts of the data set to maybe using some active learning scheme to develop new labeling functions, and we're very interested in that. We don't have that in the current system other than in a basic sense of being able to iterate quickly, but yeah, that's an exciting possibility. So I should probably move on now, but these are great questions, so we could talk about it more afterwards. I guess I'll skim by these, but some evaluation results on the TAC KBP challenge. It's a standard benchmark in relation extraction. We got some decent improvements with what we think is an easier development process using data programming. And we see improvements in both manually defined features and with, in this case, an LSTM neural network on a variety of tasks that we had previously approached using this data programming method. So let me just briefly give pointers to current directions, and you'll hear a lot more about this from other people today. So first of all, kind of two big categories. We want to make sort of keep working on this method and make users more productive by requiring less input from them. And we want to add more types of data to our roster. So goal number one, Jason's going to talk about next, so I'll just give some brief pointers, is that we want to think about how we use labeling functions to leverage domain resources like medical ontologies, like hand-labeled data sets that exist out there that maybe aren't an exact mapping onto our task, but could be leveraged. We want to move up the stack. We want to think of labeling functions as a very simple generic framework for leveraging weak supervision. And we want to think about how to build abstractions on top of this. So functions that generate labeling functions that take in maybe a medical ontology and just check for membership in different parts of it, generating hundreds or thousands of labeling functions. And therefore, this gives us a good way to increase productivity, we think, that you can't do when you're just hand labeling data. And we want to get rid of this candidate extraction stage of defining the initial facts that you consider in your binary classifier. And we're just excited because we think this new paradigm gives us room to improve vastly on user efficiency in tasks like these. And then goal number two is just expanding to new data types and seeing how what labeling functions look like in these new data types. So one is for tables. So this is sort of what we think of as semi-structured data, where you have maybe tables embedded in images or in PDFs, maybe with complex structure. And this is an example of a project that we have ongoing with Braden, who will talk later at the poster session about extracting information from parts sheets. And we also have a collaboration going on in this area where we're trying to extract from all of the tables that are often in the appendices or extra supplementary data of papers on genome-wide association studies and create a big database online that people can check their genome against. We're also interested in thinking about labeling functions for videos and images. So suppose that you have the resources to collect hundreds of thousands of hours of road data, but you don't necessarily have the resources to label all of this data. This is a concern we've heard from people in the industry. You want to leverage various sources, which could be expressed as labeling functions like crowd labels, maybe simpler models that are biased or insufficient. And we want to know if we can use this paradigm to apply to these types of scenarios. And we're also, with Professor Rubin, who's in the audience, we're starting to explore applying this to medical imaging tasks, seeing if we can use some of the standard heuristics, such as density and et cetera, to weakly supervise large conv-nets using this framework. So in summary, we have this set of problems we're very excited about extracting dark data. We think we can do this with machine learning and automated feature generation techniques if we have large training sets, and we think we can create them using this approach of data programming. And there's lots of exciting work left to do here. So we are very excited to talk with you, and thank you for your support and your ideas and your data, which we love to steal. Kidding. Okay,